So we have completed regression. We have completed all the variants in regression, including the gradient descent, the least square error method, and also the regression based on regression. So those topics have been completed in this lecture, and from now on, now 6 to 7 lectures will be around classification, in which we will be discussing what the classification is, how do we evaluate a classification model, and then we will also discuss few classification models, including naive Bayes classifier, KNN, k nearest neighbor, SVM, decision tree, and this logistic regression also. So these are the 5 different classification models that we will be discussing, maybe one or two more, but not more than that. So let's begin that what is this classification and what do we mean by this. So classification, it is a supervised learning technique that is used to identify the category of new observations. So generally what we say is, I have given multiple times the same example regarding the face recognition, that whenever we have a data set, we are trying to classify uh, that person's face, that what is the name of your friend. Let's say that you are meeting someone in your university. So I mean, it is without even any effort. If that person is your friend, your brain recalls the name of that person. Similarly, on the daily basis, we classify each and every action of ours in terms of to do it or not. Let's say that even if I want to get up from the chair, this is a decision. This is a binary classification. If I want to stand or sit, so classification we do on daily basis, and in everything we have this classification problem in the real world. So in classification a problem, a program learns from the given data set, because now this is a supervised learning technique. So we will have a data set. It might be in the Excel form, in which you are trying to classify the class of that particular values. And we have discussed one of the problem of iris dataset, in which there were uh, three types of flowers of iris, right? uh, and similarly, there can be any number of classes. For example, let's say that you want to maybe do a digit recognition, and there is image dataset. It is very famous dataset, MNIST. So this MNIST dataset is a digit recognition dataset, and in which there are lots of images. I think there are 60K images in the training dataset, and 10K images in the test dataset. If you look on Kaggle, you will find this dataset easily. And this dataset has some values corresponding to each digit. Let's say I know for a fact that there are 6,000 images of each digit. Let's say there is a image of 0, there is image of 1. This 1 can be written in multiple ways, right? I mean, it can be anything. Handwriting can be different, but it is all one. And similarly, 2, it can be like this, it can be like this. So 2 can be multiple types. So there are thousands, 6,000 of images of each type, and that image size by default is 28 cross 28 if you work on this dataset, and we will do it in the lab. In this MNIST dataset, there is this 28 cross 28 image size of the digit each photo, and this if flattened out in a single dimensional array, 1D array, this will be 784 values, right? So there will be a problem for you. If I mean, you have to solve, you have to flatten out each image into 784 columns, which will be your X, and Y will be your digit. So Y will be your digit. Is it 1? Is it 0? Is it again 1 or 2? So digit recognition will be done based on those 784 values. So it can be any number of independent variables, I mean, in this X part, and based on that you are doing the prediction. And it can also be done on the directly on the images. You can see in the figure below classification of vegetables and groceries. So there is this group of things, right? And you have to classify them into vegetables versus groceries. So because this is a supervised learning, it has to have the target value in the data set itself. So there will be classification The naming will be there, that this image is of a vegetable, this image is of a vegetable, and this is a grocery item. So that kind of thing will be there because it is supervised learning. But again, the function will remain in y equal to fx. You have to do the prediction based on the independent variables. It may be in terms of Excel sheet, it may be terms of directly images, that you are working directly on images. It is generally taught in deep learning that you are directly working on images. But in machine learning, generally what we do is we extract the features out of this image. Those features may be PCA features, it may be directly you are flattening out the pixels of the image, and you are then processing it into the machine learning model. So there are multiple techniques in this also. The most important part of classification is that the y is a discrete value. So it means that it has to be a number, 1 2 3 4 up to n, right? The class cannot be a negative number. uh, if there are, I mean, it can be in a way that you want to classify something into 1 and -1, but yes, it has to be, yeah, it has to be what we say, natural number. Yes, it has to be a natural number, and it means that it has to be kind of a all. It can be negative, it can be positive, but it has to be natural number, not the whole numbers. Whole numbers is from 0 to n, but including minus infinite to plus infinite, it can be any number of classes, but only natural numbers, not the floating numbers. So it will be a class. And there are two types of classification mainly. There is binary classification and multi-class classification. So binary is simple, two classes, 0 1, yes no, true false. And real world example is that you have to classify your email into spam or ham, spam or not spam, right? And then medically you can tell that if there is a th- I mean, maybe the disease is there or not. So let's say that you want to make a model which can do cancer classification, that if that maybe lung image has a cancer in it or not. So that kind of classification can be done, and it is a binary classification problem again. And also if there is this customer risk in terms of fraud or not. So if let's say, I mean, it is a very famous problem, credit card fraud detection. So many people do work in this domain also, customer risk analysis, and it has a use case in banking mainly, and even in the stocks. So I mean, yeah, I mean, fraud or non-fraud, this is a binary classification again. And anything else having more than two classes, it will be multi-class. If it is having greater than two classes, it is multi-class, right? I mean, two classes is binary, single class is not even a classification. It means that you are having everything in a single class. But then if there are two classes, it is binary classification. If it is a greater than two, it will be multi-class. And multi-class can be, let's say that there is this risk evaluation of customers, low risk customer, medium risk, high risk, maybe in terms of credit card payment, that person is being ranked that it is a low risk customer if he is doing the payments on time, and if it, I mean, if he is unable to do the payments, he is a high risk customer. I mean, if the bank is giving a loan of 3 lakh rupees, obviously credit card is also a loan, maybe 1 month loan it is, but still it is a loan, and you have to pay after 1 month. You have to pay whatever the bill of credit card comes. So if you are unable to pay, you will be termed as a high risk customer. And similarly, if you want to do the classification in terms of sports, politics, entertainment based on the news, or maybe some image of the person, so that kind of classifications are all coming under multi-class classification. There is this third technique, with, I mean, third class of classification. It is multi-label classification. It means that uh, let's say you are, I'm giving you one example. Let's say that you are walking on a beach, right? So there is this water behind you, and there is this evening sun also in the image. So maybe you are trying to write the keywords, maybe you are also having some more people in the image. So generally what happens is, for example, on Instagram, multiple hashtags comes up. Even in your LinkedIn post, multiple hashtags are suggested, that maybe beach is written, and maybe evening is written here, So few things can be written automatically. So when you are giving those kind of suggestions, you are actually giving multi labels to this single image. This is an image, and based on that image data, you are trying to give multiple tags to it. Is it a beach? Is it evening? Is it sea? Is the children playing? So hashtag playing can also become, can come here. So those kind of multiple tag system in real world we have seen on LinkedIn and Instagram. That is multi-level classification, and in this instance there is this text classification problem written here, that this sentence, if Virat Kohli joins politics, or maybe Saurav Ganguly has joined politics, so those kind of keywords will be given the tags of sports as well as politics, right? And this is a multi-level classification. Do you people have any doubt till now? Anyone, any doubt?
No, sir.
Okay, so moving ahead.
No, sir.
Okay. So now, why regression models are not used for classification? Before that, I want to, chalo, I will ask that later on. I have one question regarding logistic regression. But now, why regression models are not used for classification? Classification models are not useful for regression because of the following 2 points. Regression models give continuous value. We all know that regression model always gives a floating number. When we were doing house price prediction, it was giving us maybe 70 lakh or 60.5, those kind of floating numbers, right? Continuous values. And that does not give any probabilistic value. Probabilistic value means that, let's say, uh, you are getting the value of 70 or 60, so you have to manually classify the numbers. You have to put a if condition that if it is less than 50 lakhs, it is a cheap house, and if it is more than maybe 1 cr, it is a what we say, high priced high priced house, right? So this kind of classification you have to do on your own when you are working with the regression models. One second. Yeah, so in regression models it is clear that we have the continuous values, and we cannot say that this is classification, right? And the second part is that linear regression models are insensitive to the uh, imbalanced data. So it this statement means that, let's say you have you are doing house price prediction, and maximum houses are around 70 lakhs, or maybe 71, 72, and very few houses are above 1 cr. It may be 1.05, 1.0, 1.1, but maximum maybe 17 out of 20 are having prices less than 1 cr. And if you want to do a classification in this, it will be that, 17 out of 20 will be having less than 1 cr price, and only 3 out of 20 will have greater than 1 cr price. And if this kind of a condition comes up, this is what we call the imbalanced data. And generally when we are trying to train our model, we have to take care of this thing. We cannot train our model having this kind of a imbalance. I will give you real world example. Example is that, let's say that you want to train your model if someone has a cancer or not. And in medical data we all know that not everyone has cancer. It is not very common. So it might be the case that one in maybe 10,000 people is having cancer, right? And if you have, let's say, 10,000 rows, if you have 10,000 rows in your Excel sheet, and only one out of those 10,000 people you write that okay, this person has cancer, you are classifying it into one, and all the other 9999 rows have value of 0, that okay, 9999 people are not having any cancer. So uh let's say that maybe next term 1000, 10,001th term comes, 10,001th case comes and you do a prediction of 0. Okay, you say that this person does not have a cancer. Why? Because 9999 cases were 0, so your model actually thought that okay, there is no cancer and maximum cases are having 0. Maybe this is a outlier or anything like that. So that will be a problem. Why? Because if you calculate accuracy will give you, let's say you are trying for 100, I mean maybe 99, so maybe 10100. So from 1 to 100 you are trying 100 cases, and out of those 100 cases you get all zeros, right, as the outputs on the test data set. Let's say you had these 100 rows, and in all the cases your model gave 0. So even if one of the person was having cancer and it was not detected, and they said okay, even this person does not have cancer, so out of that 100 only one person is not, I mean only one person is there who is giving, who is being given the wrong answer. So still you will say that my model is 99% accurate because 99 people are not having cancer. So you are getting the output. Let's say that you are saying 0 every time, your model is saying 0 every time. It means that for those 100 cases you are saying 0 every time, so one person is wrong. It means 99% accuracy is there. So this is very high accuracy. Obviously this is very high, and someone without any experience would say okay, this if this model is 99% accurate even on the test data set, it is excellent model, right? But if you do not handle this imbalanced class problem, you will never ever be able to get the value correct for your cancer prediction. Same for the, let's say, uh, that's earthquake. Yeah, if you want to do earthquake prediction, not every day earthquakes come, right? Earthquake comes, let's say, once in a 5 years. So in 5 years there are approximately 1800 days. So one out of 1800 case will be there that yes, okay, there is an earthquake on that day, but other 1799 days you will say okay, there is no earthquake. So even if you say, if your model says okay, today it is no earthquake day, and again you are doing the accuracy for maybe 1000 days, and every time you say no earthquake you are saying 0 in all the 1000 cases, because you had trained on 1800 cases, out of which only one out of the 1800 had that earthquake as a yes, and 1799 out of 1800 was no, that okay, earthquake is not there. So your model generalized the model that okay, let's say that whatever the data is, I have to say 0 every time, because it will be in any case 1799 into 1800 divided by 1800 into 100, so nearly 99.999% accurate. So even if you are saying 0 every time, and one out of 1000 was earthquake day, but you said 0, so only this much is the error, 1 by 1000. And if you calculate the percentage, it will be 0.1%. It is very low. And again, someone with zero experience will say that okay, if even if your model is giving 0.1% error, that is very low. Okay, so you can say that your model is good. But on the other hand, we also know that this is not the perfect way to train your model, that you are not even considering this thing, that there is this very huge imbalance which we need to take care of. So I mean, I told all of these things because it is very important to handle the real world data, because especially now in the current times everyone is saying that okay, I want to be a data scientist, but in real world data you will be challenged with these kind of problems and you will have to find solution to handle the imbalanced data. So let's say now we create a perfectly balanced data set where it contains a list of customers and a label of customer to determine if the customer had purchased or not. In the data set there are 20 customers, 10 customers of age between this who purchased, and 10 customers of age between this who did not purchase. So according to a linear model, you are plotting a straight line, right? You are plotting a straight line based on the data set. So this was the data set, this was the data set, and if you implemented a linear regression, obviously linear regression line will be fitted according to this red line, right? This is my linear regression line, which will try to fit all of the data with having minimum loss. So that was the main objective of linear regression, that you have to fit a straight line with the minimum loss, considering all those things, r square value, adjusted r square value, everything. But we also know that if we want to do a classification here, we have to draw this green line, which is not possible through linear regression, because linear regression will try to calculate the best line in which there is minimum loss. So there is a big difference between regression and this classification. So that's what is being discussed here. Now after that, let's add 10 more customers age between 60 to 70. Then what will you do, right? And what we are saying is train our linear regression model finding the best line. So when your data set is like this, one is there, one is here, one is here. Now if you implement the linear regression, your line will be like this red line, okay? And again, this is not the best scenario, because just minimizing the error and fitting a line is not the purpose, but we want to do a classification, we want to get the things done. But our linear regression model in this case manages to fit a new line. But if you look closer, some customers age having 20 to 22 outcomes are predicted wrongly. So if you look into this, uh, by using this linear regression, you can easily see that, okay, this one and this one are on the right hand side of the red line, but my this section 20 to 30, these people are coming on the left side, so this does not look right. This is not the best way. So the major objective of these two diagrams were to explain you that linear regression is not always the best way to do this kind of a classification. We have to consider this classification in a different way. We have to find a new way to do this classification. Now we have come to a first model. This is my first classification model, and you will understand that why this is called logistic regression. I mean, most simply put, uh, I will show you one diagram. Yeah. So this is a S form of diagram. And in this, generally what we are trying to do is, let's say that we were trying to do a regression. And for regression, we are trying to do a prediction between 0 and 1. Just imagine this scenario, that you are trying to get a value between 0 and 1. And if that value uh, is less than zero point 0.5, you are classifying it as a 0. And if it is greater than equal to zero point 0.5, you are classifying it as 1. So you are doing a kind of round off thing, right? So this is the zero point 0.5. Here you are trying to round off that if you are coming on this side of the dot, you are coming on the left side of this zero point 0.5 value, you will be round off to 0. You will have to give the 0 as the output. And if it is zero point 0.6, 0.7, 0.8, anything, that will be round off into 1. So this kind of binary classification will be done. This is the gist of what we say logistic regression. So let's read what is being written here. Logistic regression is one of the most popular machine learning algorithms, which comes under supervised learning technique. It is used for predicting the categorical dependent variables using a given set of independent variables. Okay, so obviously we also know that y has to be predicted using the independent variables. So this is the equation. And logistic regression is much similar to linear regression, except that how they are used. Now obviously linear regression was giving us some values between it was a floating number. It was not just the natural numbers. So linear regression is used for solving regression problems, but this logistic regression is used for solving classification. So there is a very small difference between these two. And as a beginner, you might get confused that okay, linear regression and logistic regression, both of them has the word regression in it, so these are both part of regression. But you have to remember that logistic regression is a classification model. So logistic regression uses the concept of predictive modeling as regression. You are doing some kind of a prediction, but I mean, you are doing a predictive modeling in a way that you are going to round off it into that 0 or 1 part. So that so it is called logistic regression. And let's see the function. So there is this function called sigmoid. This function, uh, 1 upon 1 plus e to the power minus z, where z is my equation, but I was using in linear regression. So z was my linear regression function, right? So if you remember, this was my equation of linear regression, but that linear regression is being substituted along with this thing now. So you have to write this equation and you will say that okay, this is my prediction, and function this function is called sigmoid function. Okay, so sigmoid or a logistic function. Now because this function has name of sigmoid, that's why I mean, the sigmoid has also the name of logistic, that's why this is called logistic regression. We are using a sigmoid function, but the sigmoid also has its name as logistic function, that's why the name, this logistic regression. Okay, so the hypothesis function that maps the given values to the of the input variable to the output variable. So we were earlier only dealing with this thing, but now this equation has been updated to this part, 1 upon 1 plus e to the power minus z, where this x1, x2, x3 are my independent features, all my features that were in the left hand side of my excel sheet, and this y was my final class. But yeah, left hand side was x, so this is my x, that okay, there are multiple features that are independent of each other, and this beta 1, beta 2, beta 3 up to beta k, all of them are the coefficients. And we were only playing with the beta values in linear regression, but now we have to consider this logistic function. And this logistic function looks like this was the s curve, this is called my logistic function or the sigmoid function. This is the plot of it. And so for example, let's say that we have this equation and we were trying to solve this kind of a thing in linear regression, but then when we put it into this formula, 1 upon 1 plus e to the power minus z, for multiple types of z, answer has been given here. If z is equal to 0, then if you solve this, obviously it will be 1 upon 1 plus e to the power 0 or minus 0, and e to the power minus 0 is 1. So this 1 upon 2 will be zero point 0.5. So at z equal to 0, answer is zero point 0.5. At z equal to infinite, uh, so if I put the value of infinite in my z, so it will be 1 upon e to the power infinite, right? And 1 upon e to the power infinite will become 0, it will be 1 upon 1, it will be answer 1. So that's why z equal to infinite, answer is 1. Similarly, z equal to minus infinite, answer is 0. So that's why this curve very easily explains how the things are working. You have to just simply put the three values of z into this formula, and you can easily plot this graph and understand, okay, so I mean, you can easily plot this graph and understand that what is being done. So now the sigmoid or logistic hypothesis function gives the value between 0 and 1 that we have already understood, because of those infinite values we have tested. uh, the maximum value you can achieve is 0 or 1. And so the output of sigmoid function is considered as the probability. So whatever your sigmoid curves give, let's say that it is giving me the value of zero point 0.8 or maybe zero point 0.7 or maybe zero point 0.2, all of them will be labeled according to this rule, that if it is less than zero point 0.5, it will be uh, I mean shortlisted or maybe round off to 0, and if it is greater than zero point 0.5, it will be round off to 1. So binary classification can be done easily by using this function. And decision boundary. So if you have any doubt till now, you can ask. I will move ahead. If you have any doubt, you can ask please right now, otherwise I will move ahead. Has everyone understood that why this linear regression is not being directly used in classification? This is the first question here. Has everyone understood? Hanji, quickly.
Yes, sir.
And after that, have you understood the function of this sigmoid function? I mean, why we are using this, and how does this help us to give me the classification? I have one question here which has not been discussed by me yet. So there is this name regression in it, right? Logistic regression has the word regression in it, but it is actually doing my what we say classification work. Then why did people not name it as logistic classification? Why are we saying it logistic regression? Can anyone tell? This is actually an interview question, that why would you say this function as a logistic regression function, logistic regression problem, where we also know that it is a classification problem. Can anyone tell quickly? The reason is simple. We are directly using this linear regression statement here. Linear regression, because we used to do this linear regression uh, by using this multiple beta values, multiple coefficients along with the independent variables. Because we are using this statement into our equation, that's why the word regression is there into the logistic regression model. Otherwise we could have easily said that okay, this is my logistic classification, because we were using logistic function, we were using the sigmoid function, and we are also doing the binary classification. Maybe someone would have named it logistic binary classification, or maybe logistic classification, but we kept the name as logistic regression because we are actually utilizing that linear regression equation within this function. I hope everyone has got the point now. uh okay, so let's talk about the decision boundary. We have already discussed that if it is greater than zero point 0.1 we have to label it 1, but this is possible if and only if z is greater than equal to 0. Because if your z value is greater than equal to 0, then only this number will be greater than equal to zero point 0.5. So it will be zero point 0.5 when it will be 1 upon 1 plus e to the power, what will it be? If I want to make it as 1, it will be 0. So if my z is equal to 0, if z is equal to 0, then my answer is zero point 0.5 in this case. But if it is greater than 0, let's say 0.5 it is, right? Or maybe, chalo, let's say it is 1. So it is 1 and it will be easy for the calculation. So 1 upon 1 plus e to the power minus 1. uh, so if I solve this, it will be 1 upon 1 plus 1 upon e, and e value is 2.71 if I remember correctly. And if you solve this, it will be 1 upon something greater than 1, and eventually it will be greater than zero point 0.5. Okay, so if you try to solve this equation, you will get the number as greater than zero point 0.5 in this case. And so anything which is greater than equal to 0 for a z, it will give me greater than zero point 0.5 as the answer. That is beta naught plus beta 1 x1, everything, all of these coefficients along with the independent variables will have the value greater than equal to 0. So this z was actually this equation only. All of that has to be greater than equal to 0, then only you will get the value of greater than zero point 0.5, and it will be eventually labeled as 1. And if it is less than zero point 0.5, it will be labeled as 0, and in this case z has to be less than 0. If your linear equation is giving you value less than 0, you can simply put it in the sigmoid, this sigmoid function, 1 upon 1 plus e to the power minus z, and you will get the value which will be uh, uh, this less than zero point 0.5. Okay, so you can see this. There is an example trying to it has been put to make you understand the things. Let's see that what is being done here. So in this, you have to do a classification between the male and female. These are the two classes that you have to do. You have to do this kind of a classification, and something is being done here. Let's see what's being done. For example, in the figure, depending upon the age and length of hair, the person is classified into male or a female. So okay, age and length of hair are the two parameters. So the hypothesis function will be this 1 upon 1 plus e to the power minus z. And I mean, now examples are labeled as male 1 if this is the equation. Okay, you are labeling it as 1 if this equation is there, beta naught plus beta 1 x1 plus beta 2 x2. Can anyone tell me that why this equation has stopped at beta 2 and why we are not writing it till beta n, maybe beta 3, beta 4 up to beta n? Why there are only these I mean only up to beta 2? Why there are only 3 betas and not 4 or 5 or maybe 10 betas here? Anyone can tell?
Sir, because the criteria is age and hair, not more than this.
Yes, because we have only two parameters, age and length of hair. And we have discussed this in linear regression that if there are two parameters along with the beta naught is a constant. Okay. So for the two parameters, you will have this beta 1 and beta 2. That's what is being done here. Beta 1 for the x1, beta 2 for the x2, and beta naught will be a constant which is required. So these are the three betas that will be used in this case because there are only two variables. So this is important point to remember and understand the equation, because just by reading slides someone might get stuck here that okay, previously there were multiple betas but now only three betas are here. So this is the reason that we have only two variables, and all points above or on the line will have this equation. So okay, obviously it's just that you have moved this part on the right hand side of the equation. So now examples are labeled as male if this is the case and you have this thing, uh, and this decision boundary has been made just to make you understand. I mean, not all the calculations have been shown here, but you can see that there are some misclassifications. On the right hand side, we say that we have the males, but here two females are there, which has been wrongly classified. And on the left hand side, if we say that all of them are females, then these two are the misclassification and males have been classified into females. So this kind of a classification will help us to judge our model, that okay, so let's say that there are maybe 30 points here, but out of them four of them are wrongly classified, two for males, two for females are wrong, and if these are 30, so this is my error, and 26 out of 30 are correct. So nearly let's say it will be um, so what it will be, it should be around 88% maybe. So it will be around 88% accuracy and maybe 12% uh 12% error is there. So this kind of model, if implemented, it is still performing good. I mean 88% is a good accuracy. So now decision boundary. Now decision boundary may be any shape, linear or non-linear. So now you have seen that okay, this decision boundary, this blue line, is a straight line, but it is not the case every time. It might be a polynomial equation and it might not be straight line every time. But now decision boundary may be shape linear or non-linear depending on the z function. So uh, we choose for the sigmoid function. So whatever function we are trying to do in this thing, 1 upon 1 plus a, I mean in this 1 plus e to the power minus z. So if my z is very complex, it might lead to, I mean it will be classified into 0 and 1, but this z might be non-linear, right? I mean uh, it if it is multiple, if it is having multi-polynomial equation, this z will be affecting the this function to be linear or non-linear. And then the decision boundary is insensitive to balanced or imbalanced data. This is very important. This decision boundary does not care about if there is only 1 out of 1,000 cases as a positive case and 999 people are having a negative case. So those kind of imbalanced problems are not handled by this kind of a decision boundary, and it is characterized by I mean it is the characteristic of hypothesis function. For example, for the purchase labeling problem discussed in slide 6 and 7, the legislation when classified correctly. So yeah, I mean we have this thing, 6 and 7 slide were there, 2 3. So this equation as well as, I mean this graph as well as this graph. So in this case, that misclassification regarding the uh, what we say, so even if it has imbalanced data, that kind of a thing will be easily I mean classified using this classification, but it will have this uh, the logistic regression will be done easily. So now we have seen in that 6 and 7 slide also that in that midline equation was there and it was able to classify that two things. But now let's see, if we are doing it with the logistic regression, we have to make this S-shaped curve, and this S-shaped curve will be made according to this thing. So logistic regression model for 20 customers, balanced data. So if your data is balanced, then it will be equally distributed, and we can see that these 10 points are above and 10 points are below, and it is able to classify it into two classes using this S curve. But if it is imbalanced data, then my S curve will look something like this. If it is having these kind of two things at the bottom, then your uh, this curve will look like this. Obviously it is not going beyond one, so this one is being extended till here, because there were 60 to 70 age people and 20 to 30 age people, so it is extended and it will look something like this. It will not be symmetrical. Okay, so now logistic regression cost function. Now we will be discussing about the cost function of logistic regression. uh, so logistic regression uses the concept of predictive modeling as regression. That is, it finds the optimal value of the coefficient betas by minimizing the error. Okay, so we are just trying to minimize the error. Earlier my equation was this yi minus y hat. This kind of a square function was there, and I was doing this kind of a least square error method. But now this y hat is being expanded into 1 upon 1 plus e to the power minus z, where this z will be equal to this equation of beta naught plus beta 1 x1 plus beta 2 x2 up to beta k xik, and that's what is written here. You can see in this formula of mean square error. This was function of a mean square error. The same thing is being done, just for the, I mean, this y hat has been updated accordingly according to the logistic regression. And now this is due to the reason, if we use mean square error cost function with the logistic function, it provides non-convex outcome which results in many local minimas. Now if you plot this thing, if you plot this MSE function on the left hand side, it will look something like this on the right hand side, and it will have multiple minimas. It has multiple local minimas. This one is local minima 1, this one is local minima 2, this one is local minima 3, but this is my global minima. And we have discussed this thing in the regression also, that there might be a case that you get stuck in the local minima and you are unable to reach the global minima, because there are multiple minimas, and obviously the value having the least error will be called the global minima. Otherwise you are having four minimas here, you are having four valleys, and this is 1 2 3 4, and you have to see that which one is giving me the least error come on this scale. So on this scale, whichever is giving me the least error, it is called the global minima. So yeah, and then thus for logistic regression we use maximum likelihood cost function. It is called cross entropy function. It is very famous function, cross entropy function. In fact, it is also called log loss function. You have to remember this thing, right? A log loss function. Okay, so it looks like this, that you have to write this function as this cost or error function. It will be this minus log f of x if y is equal to 1. If my class is 1, it will be, the error will be written as this thing. And if my y is equal to 0, then my function will be written like this. And now because we are using the log function here and we are also talking about the loss, so log and loss means log loss function, easy to remember. So this function is called actually cross entropy function. It has two names, so you can write anything if asked. Where y is the actual value in this function. Okay, y is my 1 or 0, and then fx give me the corresponding predicted value, whatever my output is. So if my output is 1, let's say that my prediction actual value was 0 and predicted value is also 1. I mean, actual and predicted both are 1. So in this case my log will be f of x is 1. So log of 1 is actually 0, right? Log 1 is 0. And similarly, in that case, this second thing, if my y is equal to 0, and so it means that if my class is 0 and you are doing the prediction as 1, in that case also minus log 1 minus, so f of x, right? And you are doing the output as 1, so f of x is 1, 1 minus 1 is 0, log of 0 is undefined. So these kind of things you have to handle depending upon what is the uh, calculation coming out to be. So yeah, this is the cost function, and then cross entropy cost function with logistic function gives the convex curve with one, or with one local or global minima. So this cross entropy function will give you single minima, which might be local or global, right? And then it adds zero cost if the actual and the predicted values are the same. And obviously, we saw that if my actual and predicted were same, let's say if y is equal to 1 and you are doing the fx as also 1, so log 1 will be 0. In this case, cost is 0, right? And if in other case, if 0 was to be there and you are giving output as 1, then log 0 is not defined and it will be an issue. So that's what is being written here, that it will add zero cost if they both are same, and it will add some positive cost proportional to the difference between the actual and predicted value. So whatever the output is coming out to be, you have to uh, handle it according to the cost function. And it looks like this. Let's discuss this slide tomorrow. I think the time is up. uh, we will continue from here itself. If you have any doubt, you can ask.